Hello, students. We're looking at Chapter 11 review. And so I had a few questions come in through email. Again, this is you're preparing for the exam. So we had 4A and then a few more. So let's take a look at these kind of one at a time as they come up. So question 4A. Let's see here. So in the accompanying figure, planes alpha and beta intersect at the line AB. Okay, that makes sense. The dihedral angle called SABQ measures 90 degrees. Okay, so picture this as a wall meeting the ceiling or the floor meeting a wall. And that's all we're saying. The lines PS, okay, and PQ determine a new plane that looks like gamma. All right. So let's see here. Why is this new plane perpendicular to alpha as well as beta? Okay. So what we're doing is we are looking at the dihedral angle. Now the dihedral angle is 90 degrees. So what you want to do is picture if you picked points that were on that line, and as you can see, PQ is perpendicular to line AB and SP is perpendicular to line AB. So when you bring a plane in to cut through it, this would be like, depending on how you're looking at it, if it's on the floor, you could bring uh, a room barrier and you push that against the wall. Well, as you push that against the wall, that room barrier is perpendicular to the floor and it's perpendicular to the wall, right? Both of them are forming 90-degree angles. It's 90 degrees to the wall because PQ, line PQ, is perpendicular to AB. It's perpendicular to the floor because SP is perpendicular to AB. Okay. And it says, why is AB perpendicular to the plane? AB is perpendicular to the plane because of the definition of perpendicularity with a plane. So as that line goes through it, that line is perpendicular to any line in that plane that it passes through. So that means it forms a 90-degree angle with any of them. So if you were kind of standing up against the wall and looking at that piece, any line that is on that wall that goes through is going to form a 90-degree angle. Anything on line AB that you go through, it's going to hit that plane and be perpendicular. So there you go. So that is 4. And let's see here. Next up, I think it's on the next page. So I'm going to jump forward one page because I think the next ones were like question 20. 20. Yes. So question 20. If X equals Y plus Z, okay. Maybe need to zoom in a little bit more on this, then the lines have to be parallel. Okay, so again, we're doing a nice parallel line proof. That's our goal. Our goal is to show that they're parallel. Remember, our way of showing that things are parallel is to verify that it meets that theorem, the big theorem we talked about, which says if it's any of these special angles, then it's, if any of those are congruent, then the lines are parallel. So there we go. Let's clear that out. Okay, so I have this nice little figure here, and I want to show that if X is equal to Y plus Z, then the lines are parallel. Okay, well, notice this is the if statement. It's a little bit thick. Let me get rid of that. Go down just a little bit in size. This is the if part. So you can assume that this is true because this is the condition that has to happen. So the first thing is you're proving is you would say, well, I'm going to assume that X is equal to Y plus Z, right? That's what we're saying. It's equal to Y plus Z. So if it's equal to Y plus Z over here, I could say, well, forget about this. This is now Y plus Z. All right. Now here comes the fun. What we're going to do is we are going to draw a line that goes through this point right here. And I can't say that I want it to be parallel, right? I can't do that. Okay. Um, Well, actually, I can't say it's parallel to both lines, but I could say that it's parallel to A. And so I'm going to draw a line that's parallel to A, and I'm going to call that line something. I'm going to call it C. So now I'm going to say draw C so that A is parallel to C. Now here comes what I consider to be the fun part of this proof. Now I have a line. Maybe I can just draw the actual line like this. There it is. Okay. And I better move that up just a tiny little bit. There we go. Okay. There we go. And it is parallel to line A. Now remember, from our theorem, if it is parallel, we get all of those fun angles for free. So this angle right down here, which is marked as angle Z, has to match perfectly right here because this becomes corresponding angles. So I'm going to label that one as angle 4. So I'm going to say Z, and it looks like Z is the measure of the angle. So Z is equal to, and I shouldn't call it 4, so I don't want numbers to get mixed up. I will call that M. Okay. Z is equal to M by corresponding angles. And I believe the theorem was 11-2, maybe 11-3. Okay. So if the corresponding angles are congruent, the lines are parallel. We know the lines are parallel, therefore the corresponding angles are congruent. Okay. So now I have M right there. All right. And I know M is equal to Z. So if I take a look at what's here, I have angle X, which we know is equal to Y plus Z. Z is equal to M, right? So that means X is equal to Y plus M, which means if I bring this over, that angle X minus M is equal to Y. And here's the reason why this is such an important component. Angle M was here, right here, and X was the big one. So if I take away X, that remaining component right here, and I'm going to make that a little bit thicker, is the same as Y, because that's what it says. So we would say since X minus M is equal to Y, so now I have a Y value here, and I have a Y value up here, then corresponding angles are congruent. And we actually know then that C is parallel to B. Okay. Now notice what we started with. We drew line C to make C parallel to A. Now we have C is parallel to B, right? So if we continue that, we could then say, okay, so A is parallel to C, C is parallel to B, therefore, and this was something covered in the book, that A must be parallel to B since parallel is transitive. Okay. There we go. So that is one perfectly legitimate way to demonstrate why that all works. If you wanted to, how else could you do it? If I was a student, and I was on a test and I didn't think of that, I get you could extend the lines down. And so then I would know angle Z would be the same as this angle over here. And if X is equal to Y plus Z, so this right here is Y plus Z, then the angle on the other side, this green dot, would be 180 degrees minus Y plus Z. But one of the angles down here is Z, And if it's a triangle, it has to add up to 180 degrees. So this little angle right here has to be y. And then you could say, aha, if this angle is y and this angle is y, then corresponding angles are congruent and B is parallel to A. So you could do it without drawing another line in. But since they told me it's y plus c, sometimes that extra line is really helpful. But two different ways to do it. All right, there is number 20. Let's take a look and see what else do we have here. 23. All right, we'll take a look at number 23. And is that on this page? Oop, next page. 23. Sketch 3 planes that intersect in a point. Okay. And let's see here. Given 10 points in the plane, no 3 which are collinear. How many triangles can we draw on whose vertices are the given points? All right. So we've got sketch 3 planes that intersect in a point. I guess that's just like the edge of a room. That's what I would be thinking of. It basically, if you're looking to just kind of sketch that, it would be like sketching one of these little cubes, just one of them, because you can see here in this point, I have a front face, a side face, and a top face, and they all intersect at a single point. Okay, given 10 points in the plane, no 3 of which are collinear. Got it. How many triangles can be drawn whose vertices are the given points? That are these points. Okay, so 10 points, no 3 of which are collinear. So that's the big part right there. And honestly, if I saw this question on a test, I probably would not do that question as the first step. I'd probably start a little bit smaller. I would probably start not instead of 10 points. Why don't I start with 3? So here's 3 points. They're not collinear. How many triangles can I draw? One triangle from those 3 points. Okay, so now I'm going to do 4 points in the plane. Again, no 3 of them. I can't put another one here because that would be in a straight line, so that's a violation. So I'll just put 4 of them. Kind of looks like a square, but that's fine. How many triangles can be drawn whose vertices are the given points? So I need them to be the given points. So I could say, here's a triangle. There's one triangle right there. That's like ABC. So if I label them here, ABC, right? I could have a second one that would be A, B, D. Okay. So I have A, B, C, A, B, D. Okay. And then are there any other triangles that aren't exactly the ones that I have listed? Yeah, because I could also have A with C with D. Let's take a look at that one. And I'm going to make my line just a little bit thicker so it shows up really nicely. A with C with D. Okay, so I can see 3 different triangles right there. And there is one additional triangle that I have not made yet. I'm going to change colors one last time. I think I'll go to orange. And that would be, now I'm done with all the A pieces. Now I make a B to C to D. So that would be my last one. B to C to D. So up here we had A, B, C. Down below, I kept the A, B, C, but I added some more. So this is one of these, 1 plus 2 plus 3. All right, so 1, 1 plus 2. If you go to the next one, just don't pick them in a line. That's fine, right? So then if you're thinking about these, you can start to say, wait, do I need to actually draw all the triangles? Because a triangle is formed by any 3 of these points. So I could say ABC, fine, there's ABC, and ABD, and ABE. So I've got all of the ones that have an A and a B in them. Okay, next up, I'll pick the A with the C. So ACD, ACE. Okay, that looks good. And then finally, let's move on down. A with a C. Let's go with A with a D. A with a D and the letter I haven't done before would be ADE. Look at this. The reason I'm writing it out this way is I can see there's 1 here, 2 here, and 3 here. 1 plus 2 plus 3. That's all of the ways that I can do this when I have A, B, and C. But that's all of these. Every one of these includes A. So now what you can do is say, okay, well, wait a minute. What if I removed angle A? Okay, remove point A and go and do the rest of them now with B, C, D, and E. And you already did that problem right up here, and you found that it was 1 plus 1 plus 2. So it's basically 1 plus 2 plus 3 plus 1 plus 2 plus 1. So if I wanted to do that for 10 points, I could simply write out, I see the pattern now. I don't have to keep doing it. Use the recursive nature of this. Okay. Let's see here. And yeah, that is probably pushing it for a test question. I don't think I'd do 10, right? Not certainly not on the timed portion. I might do a couple points in the plane, so maybe 5, maybe 6 points in the plane at the most, but then that's it. And we've seen this pattern though. This pattern is not something new. That pattern's come from a couple of the other questions as well. So same pattern. 23 and 24. Let's see here. The question was on D. Okay. And D says the total number of diagonals is 4860. All right, well, we talked in class about how to make diagonals. So now if you are making diagonals on a polygon, we don't know how many sides are in the polygon. So we just know the number of diagonals. So if you remember the number of diagonals, if we were doing, and I'll take we'll take a hexagon here. So remember when we were doing diagonals, how many total diagonals? We could not count. So if I start at this point, I could not count the 2 that were coming off of it because those weren't diagonals. So then I would have 1, 2, 3. And what we did is we said, hey, it looks like there's 3 for every point. If I go to the next one, I could put 1 up here and say, okay, don't count that, don't count this, because those are right next to it. And then I'd have 1, 2, 3. Then you can move to the next point. And you'd say, okay, here I'm now at this point, and don't count this and don't count this. But here we go. 1, 2, 3. Now, if you notice, the first one I drew is actually the same one that I had before. But the reason why I let that happen is that way I can move my way all the way around, and every single diagonals is just going to get counted twice. So every point has n minus, you think about how many I'm connecting to, 1, 2, 3. I have n minus 3 connections, and I do that for every point. And then I cut it in half because I would be double counting everything. So the total number of diagonals is 4860. So if you want to find the value of n, you could just plug in 4860 here, and then use a little algebra. So we can multiply both sides by 2, and that would give us 9720. And over here we have n squared minus 3n. Now, depending on your background here, you could bring the 9720 to the left-hand side and do some factoring. You could use the quadratic formula. There's a lot of different ways to do this. But the other way that I think would be really good to understand is when you're squaring numbers and getting big numbers, the fact that you're subtracting a little bit, the thing you're subtracting is so small. Let me give you an idea. If n was 100, then I would have 100 times 100, which is 10,000. But look what I'm taking away. I'm taking away 3 times 100, which is 300. I'm taking away 300, right? But I'm starting with 10,000. So my guesstimate for this would be, I'm going to estimate quickly. I'm just going to say, let's just look at the n squared. When is that close? What square number is really close to 9720? And if I were you, jump into Desmos or whatever you have. Desmos, we'll do graphing calculator over here, and we'll see here SQR, square root of 9720. And it says here it's 98.59. Okay, so what does that tell us? It tells us we're pretty close. We're going to say n is pretty close to 98. So what you could do is come in here and put in 98 and then maybe put in 99 because it's kind of between those two numbers. Let's see what we get here. So let's see here. 99 minus 3 times 99. 9504, right? And 100 minus 3 times 100. I get 9700. So that's really close to that number for an n-gon. And let's see here. Oh, I forgot to divide by 2, didn't I? Oh, no, I doubled it to get 9720, I guess. I guess I should say it this way. If you want to do n minus 3 times n divided by 2 and get 4860, just put a divide by 2 in there. So this is 4850. So I could try putting in a 101 and I get 4949. So 100 gets me 4850. 101 gets me 4949, which is over. So I gotta say, yeah, I don't think that's actually possible. The regular polygon does not exist because I tested a 99 sided figure, I tested 100, and I'll never hit 4860 right on the nose. So this is one where they would say it does not exist. And it does say determine the number of sides of a regular polygon with the stated property. So we can now say that there is no regular polygon where it has 4,860 diagonals. Okay, it's pretty cool. There's 23, 24, and anything else? 32. Okay, let's take a look at 32. 32B. Carefully draw nets that can be folded into each of the following. Cut out the nets and fold them. You will not be having to do that on the exam. I'm not going to have you actually cutting those out. But if you wanted to, if you're trying to figure out, well, how can I do that? How can I draw the nets? A square pyramid. So the first thing you want to do is build yourself the square. Then, and I will do my best on this one, I want you to think about that pyramid like we saw in class. The square had pyramid triangles coming up to the apex on each one of them. So build it so that you get kind of a triangle on each of these, right? And then each one of these folds up so that the tippy top point of each one of these, when you fold those together, comes up to form the pyramid. And that would be, there's your net. Remember, your lateral faces on a pyramid are going to be triangles, so that's perfectly fine. And if you wanted, you could, depending on how tall you wanted the pyramid to be, you could make the lines come out quite a bit further for all of them. And all it means it's just it's a taller pyramid. So let me just double check. I feel like I hit all of those. Oh, I guess I did 31B. Oh, well, still good to know that. And let's see here. 32. Draw as many nets as possible that can be folded into an open cube, a cube without a top. How many different nets are possible in part A? So again, as you're looking at nets for these, let's see here. So this one would be, I'm going to fold it into a cube. So they're only going to have squares. So you're going to have square right next to a square, right next to a square, right? And then that last one didn't look like a square, but we're just going to, your drawing's got to be as good as mine. So there we go. Okay, there's 4 of those. So if I was to fold those together, that would form like the lateral faces, and I need this to be an open cube. So I got to have one that looks something like this. And the reason is that's a bottom. So this one just doesn't have a top, so there's no top. And there would be the piece that I have. Now the question is, how many of those can you make? Well, you need to be able to fold it up to form the actual open face cube. So again, this one would be fine, but you could, oh, let me see here. Can I grab this? Oh, there we go, and move it over. Couldn't you put this here? That would be a different one, right? And couldn't I put it here and make that like look like a different net, even though it will fold up and be the exact same? Sure. And let's see here. And maybe over here, could do the same. Now you might say, oh, wait, Scott, but couldn't I also bring that up to the top up here? And I say, you're right. Yeah, you could bring that up here. But if you think about the symmetries that we talked about, having the box down here, thinking about how it goes over and down would be exactly the same net as having this one up here, because if you kind of turn your head upside down, it's going over and down. So it's the exact same net. So I wouldn't call that a different net. Okay. So there's a few of them. Question is, could I get by with doing um, anything different than that? And just realize you need it to be a open cube. If it was a closed cube, we might have a lot more options, but this one has to be an open cube. Okay. All right. So there's my nudge in the direction on that one. And I think that takes care of all the questions that came in to me. Hope that helps. I'll see you back in class shortly. All right, off you go.